There are two ways to achieve dimensionality reduction. First, feature selection. This method involves identifying the features that have the least predictive power and dropping them all together. Therefore, feature selection involves identifying a subset of features that is most important. An important distinction of feature selection is that it maintains the original meaning of every retained feature. For example, let's say we have a housing dataset with price, area, and number of rooms as features. And if we drop the area feature, the remaining price and number of rooms features will still mean the same. In contrast, feature extraction is a transformation. Feature extraction takes an m-dimensional data and transforms it into n-dimensional output space, and usually m greater than n. However, it retains most of the information, and in doing so, it creates new features that have no inherent meaning. For example, if we look at the same housing dataset and use feature extraction to output it into 2D space, remember it was a 3-dimensional dataset. So the new features will not mean the same as price, area, or number of rooms. They will be devoid of any meaning. Feature extraction method is also useful when the variables are highly correlated. If you look at the plot, low redundancy in the top right, and compare it with the high redundancy in the bottom right, you'll notice the feature extraction will be more relevant to the dataset that display high redundancy tendency. The type of principal component methods depends on variable type contained in dataset. We have principal component analysis, PCA, which is one of the most popular multivariate analysis methods. And the goal of PCA is to summarize the information contained in a continuous quantitative multivariate data by reducing dimensionality without losing important information. Correspondence analysis, CA, is an extension of the principal component analysis for analyzing a large contingency table by two qualitative variables or categorical data. We have multiple correspondence analysis, MCA, which is an adaptation of CA to a data table containing more than two categorical variables. Factor analysis of mixed data analyzes dataset containing both quantitative and qualitative variables. And finally, multiple factor analysis is used for variables that are organized into groups, and we have qualitative and or quantitative variables. Principal component analysis, a technique proposed by Pearson in 1901. Pearson recognized that in many problems there's a variability in the predictor variables, and he developed PCA as a technique to model the variability in the predictor variables. So the aim of the method is to reduce dimensionality of multivariate data and preserve as much as relevant information as possible. And we can say it's a form of unsupervised learning because it relies entirely on the input data. Note that dimension means variable. To illustrate the concept of PCA, let's look at the data set with three features or three variables plotted in a three-dimensional space on the left. After applying PCA, the original data points can be reduced to two features, and they can be projected into 2D plane. Then PCA performs the compression by projecting the dots onto the lower dimensional subspaces. Note that this 2D subspace is spanned by orthogonal or perpendicular vectors, and they call first principal component PC1 and the second principal component PC2. The first principal component holds the maximum possible variance. The second principal component, orthogonal to the first principal component constructed, it also uncorrelated to it, and defined the next dimension which hold the maximum variance. So the original data can be further reduced to one feature into 1D line. The original data instances can be compressed by projecting points down into 1D line, which is defined by PC1. So PCA can be described as type of transformation, which is performed with the goal of dimensionality reduction. And also, it can be used as a part of pre-processing and a part of exploratory analysis to understand structure of data. It helps us identify hidden pattern in a data set and also identify correlated variables. For example, if a different machine learning training algorithm that you're running is taking too long to run, then PCA can be used to reduce number of features, which in turn reduces the amount of training data and time to train. So here we can say that PCA can be used as a pre-processing step as a part of larger workflow. What is principal component? It is a normalized linear combination of original predictors in a dataset. And the principal component can be written as this formula. Z is the first principal component. Phi is the loading vector comprising of loading Phi1, Phi2 of first principal component. The loadings are constrained to sum of square equals to 1 and also defines the direction of the principal component Z. So it results in a line of p-dimensional space which is closest to the n observations. The closeness is measured here using average square Euclidean distance. X1, XP are normalized predictors. Normalized predictors have mean equal to 0 and standard deviation equal to 1. Note that response variable y is not used to determine the component direction. Therefore, it is unsupervised approach. So the first principal component captures the maximum variance. The second principal component captures the remaining variance. And together, first and second principal component are uncorrelated. Their direction should be orthogonal. See graph on the right. Notice the direction of the component, as expected here, orthogonal, perpendicular. And this of course suggests that correlation between them is 0. Computing principal component can be understood as an optimization problem. Here we have 3 data points, blue dots, and they placed in the 2-dimensional space. The first principal component, PC1, can be any one out of, let's say, infinite number of lines that occur in a space. So we need to select a candidate line for projection. Here, candidates are gray lines. And PCA optimization can be seen as a problem of selecting the line that minimizes the total projection error, also known as the reconstruction error. The red line indicate orthogonal perpendicular projection error here, and the green segment indicate variance or spread of data projected onto candidate axis. Let's look at the rightmost figure. It shows an axis that produces the smallest total projection error, at the same time the largest variance. So this axis would be chosen to be the first principal component. This line minimizes the sum of projection errors. Difference between residuals in regression on the left, which are vertical lines, and projection error in PCA, which are perpendicular 90-degree lines. Recall that residual measure how well line fits in individual data points. Variance and covariance measure of the spread of set of points around the center of mass, or their mean. Variance is a measure of deviation from the mean for points in one dimension. Variance is calculated as the average of the squared differences of the value and the mean of the value. Covariance is a measure of how much two variables change together. It is a measure of the strength of the correlation between two sets of variables, so it works in 2-dimension space. If the covariance of two variables is 0, the variables are uncorrelated. A covariance matrix describes the covariance between each pair of dimension in a dataset. For instance, if we have three variables, we have three dimensions and it will be 3 by 3 matrix. Let's look at the covariance matrix here. So we have three variables, three dimension, and it is 3 by 3 matrix. The diagonal value represent the variances of each dimension, x1, x2, and x3. A large diagonal value corresponds to strong signal, and we would like to maximize these variances. The off-diagonal values are the covariances. Very large off-diagonal values correspond to high distortion in our data, such as correlation, redundancy, and we would like to minimize them. So covariance matrix defines the shape of our data. Diagonal spread is captured by covariance as we've seen it, and a variance is captured an axis-aligned spread. We can say the covariance matrix defines both the spread, variance, and the orientation, covariance of our data. If we would like to represent the covariance matrix with a vector and its magnitude, we should simply try to find the vector that points into the direction of the largest spread of data, and magnitude equals the variance in this direction. The eigenvectors, principal components, determine the direction of the new feature space, and eigenvalues determine their magnitude. In other words, we can say the eigenvalues explain the variance of data along the new feature axis in a smaller reduced dimension dataset. For PCA, data must be numeric. Any categorical features must be converted to a corresponding Boolean integer feature. First, the value in the original dataset must be scaled and centered to prevent features with large numeric ranges from dominating other features. Here's an example of PCA analysis with unscaled on the left figure and scaled predictors on the right figure. This is a dataset with about 40 variables, but you can see on the left, the first principal component, which is marked PC1 on the x-axis, is dominated by one variable item. And the second principal component is dominated by another single variable item. This domination prevails due to high value of variance associated with those variables, so we need to scale them. In the second step, we calculate covariance matrix. We decompose covariance matrix and extract eigenvectors and eigenvalues. Then we select the largest eigenvalues in eigenvector. We'll start by normalizing our predictors by subtracting the mean from each data point and dividing by standard deviation. As we mentioned, it is important to normalize variables, as original predictors can be on a different scale and can contribute significantly toward variance. And of course, this will lead to large loadings for variables with high variance and to dependence of principal component on the variables with those high variance. We also need to drop our y variable and then scale our value. So they will be set typically to the mean equals 0 and standard deviation equal 1. As illustration, we'll be using a dataset iris. Our iris dataset is stored in form of 150 by 4 matrix, where the columns are different features, and every row represents a separate sample. So each sample row X can be actually pictured as a 4-dimensional vector. We can use cov function, but in this case we need to transpose our matrix from 150 by 4 to 4 by 150 dimension. We can also extract variances. Remember, there was diagonal values of the covariance matrix. In order to decide which eigenvector can be dropped without losing a lot of information, we need to inspect eigenvalues. We can extract eigenvalues by using eig function from NumPy or eigen function in R. Now we can inspect our eigenvalues. So eigenvectors with the lowest eigenvalues bear least information about distribution of data. So those are one that can be dropped. And a common approach would be to rank eigenvalues from highest to lowest in order to choose the top k eigenvectors. Let's look at the built-in PRComp function in R, which facilitate drastically our workflow, as we can set up directly a lot of parameters such as scaling and centering. We're going to apply our PRComp function to dataset that we already scaled, so we don't need to set scale equal true. We just keep it as default. In our next step, we're going to print a summary of our principal component analysis. Summary display first the standard deviation of the principal components. This is square roots of the eigenvalue of the covariance matrix. The row of rotation matrix contain coefficients for the variables, and the rotation matrix here it's 4 by 4, number of principal components and number of variables. The rotation matrix column contain the eigenvectors, and number of principal component in rotation equal number of variables in the dataset. We can present each principal component as a linear combination of the original variable weighted by a vector. And here's an example of principal component 1, where we take loading for sepal length, sepal width, petal length, and petal width, and sum those values. Recall similar to factor analysis, we need to look at the proportion of variance and cumulative proportion, and we can use scree-plot. And rule of thumb here is to keep number of component that explains about 80% of variation. If you look at the summary, we have standard deviation, proportion of variance, which show share of the total variance in a data explained by a given variable, and cumulative proportion, which can be seen also the scree-plot on the bottom. So we notice that principal component 1 and 2 are the most relevant. How do we interpret principal components? First, let's look at the biplot on the left. All 4 variables are presented as vectors, and direction and length of vectors show how each variable contribute to components. So we would like to see the longer length of vector, and we also need to note whether direction is positive or negative, or whether the variable is close to 0. So if you look at x-axis on the left plot, which is PCA1, we notice that sepal width variable is very close to 0, and also it has a negative direction. The other 3 variables are much stronger, and they are all positive. On y-axis, which is PC2, only sepal width is shown, but also show negative direction. The other 3 variables are close to 0. We can also visualize the same interpretation using library factor extra and core plot. As you notice, dimension 1 show that the petal length, petal width show much stronger contribution. In dimension 2, we have only sepal width that show strong signal.